In our simplest way of drawing carbon-carbon double bonds, we simply draw them as two lines. And this works well for explaining a lot of organic reactions. For example, the first step of electrophilic addition that I've shown here. We simply draw an arrow from the double bond to the electrophile, indicating a bond is made, and showing where the electrons come from, the pi bond of the alkene. When we want to more clearly show what this pi bond looks like, sometimes we lay it on its side and show the adjacent p orbitals. Here's the same molecule with two adjacent p orbitals. And each one has an electron to contribute, so they share a pair of electrons. And we simply draw lines between these lobes to indicate that, yes, in this region between the carbons, but above and below the plane, not in the plane, p orbitals overlap to share electrons. This model is perfectly sufficient for a lot of organic chemistry that we wish to describe. But there are some important aspects of alkenes that kind of a model just simply fails to explain. In these cases, when we think about alkenes in the context of molecular orbital theory, we find that we have explanations for all the kinds of alkene chemistry that we otherwise can't explain at all. For example, this conjugated diene is more stable than a very similar molecule that has isolated double bonds. Why is that? And it turns out that alkenes absorb in the UV or visible spectrum. What's going on there? And thirdly, there are some reactions called paracyclic reactions that turn out to be cyclic additions between two alkenes. Some occur and others don't. They look extremely similar. Very difficult to guess why some would occur and others not using our current atomic orbital overlap theory, but molecular orbital theory lets us easily decide why some work and others don't. So for these reasons, it's worth taking a look at MO theory as applied to alkene pi systems. And with remarkably simple graphic illustrations, we can understand all of these properties that otherwise couldn't be explained. First, let's look at a few key tenets of MO theory. The key insight is simple. In molecules, we should have molecular orbitals. The regions in space where electrons should be found shouldn't be necessarily described by looking at atomic orbitals, which are restricted to atoms, but rather should look at the region in space of the molecule. So the thinking is, let's talk about molecular orbitals, and let's not be limited to atomic orbitals. The number of molecular orbitals for a pi system is equal to the number of overlapping atomic orbitals. So you count the number of p orbitals on adjacent carbons, and that will tell you the number of molecular orbitals you should expect that pi system to have. So for an alkene, there should be 2 molecular orbitals. For a diene, there should be 4 molecular orbitals. And thirdly, there are 3 types of molecular orbitals in terms of their energetics. One type is called bonding. These are lower energy than the standard p orbitals that are overlapping. There are non-bonding molecular orbitals, and they have the same energy as the p orbitals that are overlapping and don't really contribute to bonding. And the third are higher energy, and these actually destabilize the molecule if, in fact, there were electrons in the antibonding orbitals. Let's apply this thinking to a simple carbon-carbon double bond. Each carbon has a p orbital associated with this double bond. There are 2 atomic orbitals, so there will be 2 molecular orbitals. Let's draw in the atomic orbitals at some arbitrary energy along this energy axis. And you'll notice that I've taken special trouble to distinguish the phases, blue and green, of each p orbital. Each p orbital has a separate lobe and each one has an opposite phase. I've drawn these things with the phases oriented in the same direction. You'll see for some things it's very important to notice the phase of the p orbitals. And I've drawn in 2 dashes to indicate the energetics of these 2 p orbitals. Now we have 2 p orbitals that are adjacent to each other. These are atomic orbitals overlapping. So the theory says we should have 2 molecular orbitals. They'll have energetics that are lower, that's the bonding orbital, and higher, that's an antibonding orbital, relative to the overlapping p orbitals. And the distance that is moved up in energetics and down in energetics will be equal. Pictorially, we can represent these two molecular orbitals as being a combination of the p orbitals in phase, like I've shown here, and out of phase. Here they are. The bonding orbitals are when the two p orbitals overlap to form a molecular orbital, are in phase, and the antibonding orbital is when these orbitals are out of phase and therefore don't overlap. So this is our bonding orbital. This is antibonding. If we'd like to get a picture of what this means physically in the molecule, we can write in two carbon atoms tied together by a sigma bond, that's the line between them, and see that these in-phase interacting p orbitals lead to a region of space in the molecule above the pi system and below the pi system, where we'll find electron density. This is very similar to the picture we get from our overlapping atomic orbital system, isn't it? On the other hand, here's something new. The antibonding orbital occupies regions of space that are not between the two carbons, and therefore don't contribute to bonding at all. These orbitals are out of phase, they won't overlap, and if electron density is in here, it will be repulsive, so it will actually destabilize the molecule. Our atomic orbital overlap theory doesn't say anything about the existence of this higher energy orbital or where it is. So now we have a new insight from molecular orbital theory. The alkene double bond has two orbitals, one that looks very much like the one we've been talking about. That's a bonding orbital, and a higher energy one that is quite new to us. You'll see that it turns out to be important to notice that we have this higher energy one. Take a look at this. When you put electrons in orbitals, you use the Aufbau principle that puts a pair of electrons in each orbital going from the lowest energy up. And an alkene has two pi electrons it needs to accommodate, so both of those electrons will be accommodated in the bonding orbital. It turns out this changes when alkenes absorb light. The absorption of light specifically excites one of the electrons to go from this more stable bonding orbital to the antibonding orbital. Higher energy, less stable. And the wavelength of light that's required for this is equal to the difference in energy between the bonding orbital and the antibonding orbital. Now, just to fill you in on some terminology, these orbitals often are numbered as pi 1 and pi 2, and so on as you move up from the lowest energy to the highest energy. And the ones that are higher energy than the p orbitals, the antibonding orbitals, are indicated by a star. So we have pi 1, which is bonding, and in this case pi 2, which is an antibonding orbital. In addition, we notice that in the normal state, this orbital is the highest energy orbital that has electrons in it, so it's called the highest occupied molecular orbital. And this orbital is the lowest energy orbital that doesn't have electrons in it, so it's called the lowest unoccupied molecular orbital. When light is absorbed, the excitation is a result of promoting an electron from the HOMO to the LUMO. And the energy gap between these two determines the wavelength of light that's needed to excite that alkene. This will become important later as we think about dienes and trienes and their behavior with respect to absorbing light at different wavelengths. And finally, just in case you're wondering, how do they know where these molecular orbitals are in space relative to the atoms in the molecule? The answer is simple: from calculations. There are people that do quite amazing calculations that determine exactly where in space within the molecule these orbitals exist and their energies. So although I've depicted these energies in a relative sense, exactly where they are in a quantitative sense can be done from calculations. So there we have it, a molecular orbital theory picture of alkenes. Next, we'll take a look at the picture of conjugated alkenes that molecular orbital theory gives us. and learn from that what it can tell us about the behavior that otherwise we couldn't explain.